Hello there, this is Rebecca Weaver, and I'm going to be talking about derivatives today, section 1.7. Now we'll look at an example. We're going to be differentiating various independent variables. We're going to find the first derivative of capital T equals the quantity 1 plus 2t squared plus t cubed. Now in our function we have lowercase t's, and we have that it equals an uppercase T. We're going to first note that the independent variable is lowercase t and that the dependent variable is uppercase T. This is significant because they're two totally different variables. Just as x and y are different from each other, we now proceed to differentiate the function. So we have our function, our given function from the very beginning, and what we're going to do is differentiate that original function with respect to our independent variable, lowercase t. And to do that, we're going to start by separating this into sums, and then we're going to take the derivative of each particular quantity. So I'll be taking the derivative of 1 plus 2t quantity squared, and then the derivative of t cubed separately using that sum rule with respect to lowercase t. And I'm going to use the power drop rule along with what's called the chain rule. So I'll drop my 2. I'll have 2 times 1 plus 2t quantity raised to the first because I will need to drop that power by 1. Then I need to take the derivative of the function that was inside. So I'll take the derivative of 1 plus 2t. And then taking the derivative of t cubed, I will get 3t squared using that general power rule. Finishing my differentiation, when I take the derivative of 1 plus 2t, I just get a plain 2. I need to clean this up a little bit. So when I simplify, I have that the derivative is 4 times the quantity 1 plus 2t, and then I'm going to add to that the quantity 3 plus t squared. And then if I multiply that out, I will get 4 plus 8t plus 3t squared. All right, let's look at another one where we're going to take both the first and the second derivatives. We're going to look at some function, and this is a function of capital P, and it's going to equal the quantity 3p plus 1, all raised to the 5th. So let's write our given function, and then I'll begin taking the first derivative by using that power drop rule. I'll bring down my 5, and then I will multiply it by what the derivative of the inside was. So the derivative of 3p plus 1 is 3, so I'll multiply that 3 times 5, get 15 times the quantity 3p plus 1, all raised to the 4th. That's the first derivative. Simplified, it's beautiful. To take the second derivative, I'll just take the derivative again, just as if it were a brand new thing. So we'll take the second derivative, take the derivative of that first derivative. Once again, I'll use the power drop rule, bring down that 4, multiply it by the 15, and I'll get 60. And then multiplying it by the derivative of the inside, so that would be 3 times that 60 would be 180. Using that power drop rule, I'll get times the quantity 3p plus 1, all raised to the 3rd. And that's the simplified version of the second derivative. This particular example asks us to compute the following. They want us to compute the second derivative of 3x to the 4th plus 4x squared, and then they want us to evaluate this at x equals 2. So all that means that we're going to do is we're going to take the first derivative, then we're going to take the second derivative, and then we're just going to plop in a 2 for x. So here we are, we're computing the first derivative. When I take that first derivative with respect to x, I'll get 12x cubed plus 8x. Computing the second derivative, I'm going to once again use that power rule combined with the sum rule, and I'll get 36x squared plus 8. Now I just need to put in a 2 for x, and that will have me evaluating this at x equal 2. So when I plug in a 2, I'll get 36 times 2 raised to the second power plus 8. And computing those numbers, I will get 152. And that is evaluating this at x equal 2. What I've just done is computed the derivative as a rate of change. We write this as f prime of a equals the rate of change of f of x at x equal a. So if you're asked to compute a problem where they say compute f prime of a, that's all you're going to do. And if they're asking you a word problem, they might ask you to compute the rate of change. And once again, they're asking you to compute the derivative and plug in a value if they want it at a particular point. So let's look at a word problem here. So we have this example. Let S of X represent the total sales in thousands of dollars for month X in the year 2005 at a certain department store. Represent each statement below by an equation involving S or S prime. Question A. The sales at the end of January reached $120,560 and were rising at a rate of $1,500 per month. Well, first off, since the sales at the end of January, now we're going to have January since it's the first month, be x equal 1, reached $120,560. And S of X represents the amount of sales for a given month. So we're going to say that S of 1 equals 120,560. Further, since the rate of change of sales, the rate of change means derivative. So for the month of January, it's a positive 1,500. What we're going to write is S prime of 1 equals 1,500. Nice. So we're going to play again. At the end of March, so that would be x equal 3, the sales for this month dropped to 80,000 and were falling by about $200 a day. Use 1 month equals 30 days. So what we're going to have for this one is at the end of March, the third month, x equal 2, the sales dropped to 80,000. Therefore, sales for the month of March was 80,000. That just means S of 3 equals 80,000. Additionally, since the sales were dropping by $200 a day during March, this means that the rate of change of the function of S of X was 30 days, was minus $200. That means we have negative $6,000 per month. Therefore, we have S prime of 3 equals negative 6,000. All right. Additional cost. So we're going to do something a little different now. We're looking at marginal cost. Additional cost is going to be capital C of A plus 1 minus C of A. This is about equal to the derivative of C at A. All right, so we're going to get an approximation here. So the definition of marginal cost is if C of X is a cost function, then the marginal cost function is C prime of X. The marginal cost of producing A units, C prime of A, is approximately equal to C of A plus 1 minus C of A. That's just C of A plus a little bit, which is the additional cost that it's incurred when the production level is increased by 1 unit from A to A plus 1. So A and then a little bit. So A and then a little bit is basically equal to about the derivative at A. So let's look at an example. Let C of X be the cost in dollars of manufacturing X bicycles per day in a certain factory. Assume that C of 50 equals 5,000 and C prime of 50 equals 45. Estimate the cost of manufacturing 51 bicycles per day. So we know what the exact number is, and then we know what the slope is. So we'll first use the additional cost formula for manufacturing 1 more bicycle per day beyond the cost of producing 50 bicycles per day. So we already know it costs 5,000 to produce 50 bicycles per day since C of 50 equals 5,000. So if we want to determine how much more beyond that 5,000 it costs to produce 51 bicycles. Additional cost is C of A plus 1 minus C of A, and that's going to be about the derivative at A. So we're just going to plug all of that stuff in. So CF50 plus 1 minus CF50 is going to be about equal to the derivative at 50. So CF51 minus 5,000 is about 45. Solving that for CF51, we have that CF51 equals 5,045, just about there somewhere. Therefore, we estimate the cost of manufacturing 51 bicycles to be about $5,045. We can broaden this into marginal revenue and marginal profit. So we're just going to do the same thing. We're just going to say that we can do it for both revenue and profit too. So the definition of marginal revenue and marginal profit, if R of X is the revenue generated from the production of X units of a certain commodity, C of X, it's the cost function, and P of X is the corresponding profit. The marginal revenue function, R prime of X, and the marginal profit function, P prime of X, is going to be, now we need to recall that profit is revenue minus cost. So that means R of A plus 1 minus R of A is about equal to R prime of A. Likewise, profit of A plus 1 minus profit of A is about equal to P prime of A. So let's look at a problem and we'll do that. Suppose the revenue from producing and selling X units of a product is given by R of X is 3X minus 0.01 X squared dollars. Find the marginal revenue at a production level of 20, and then we're going to find the production levels where the revenue was 200. So since we're looking for marginal revenue at a production level of 20, we have an equation for R of X. We just simply find R prime of 20. So we have to find R prime and then plug in a 20. So we take our given revenue function, we take the derivative, so just taking the derivative of 3x minus 0.01 x squared, that's going to be 3 minus 0.02 x, and then we're going to plug in a 20. So we're just going to evaluate that marginal revenue function at x equal 20. Plugging in a 20 for x, we're going to get 2.6. Therefore, the marginal revenue at a production level of 20 is 2.6. Now let's go ahead and find the B part of this. We need to find the production levels where the revenue is 200, and we need to use the revenue function and replace revenue R of X with 200 and then solve for X. So we take our revenue function, and then we're going to replace the R of X with 200. Then we're going to solve for X. So this is just solving this quadratic, and we can solve the quadratic any number of ways. We could use the quadratic formula here. Here what I did was multiply everything by 100, and it factors very nicely. We get x equal 100 and 200. And then we find that the production levels for which revenue is 200 are x equal 100 and 200 units produced. And that concludes this section of our homework and our content. So if you have any question about that, be sure and email me. And thank y'all for listening and have a wonderful day.